To solve a problem using the chain rule. Now, I haven't written out the whole problem, so I'm going to say it kind of out loud to you. They have an equation here, and this equation is representing carbon monoxide in a community, and the carbon monoxide is technically determined off of our population P. Okay? So our carbon monoxide depends on what the population is in the community. This equation models how much carbon monoxide per parts per million will have depending on your population. Now your population T years from now. Okay? This is the second part of the equation. The question asks us to find out what the carbon monoxide level will be changing at with respect to the population 3 years from now. Okay? So what that means is population 3 years from now is our population is a model in terms of time being in years, and our population is changing at this rate. Okay? So 3 years from now will give us a value for T. So T we're able to figure out what our population is changing at 3 years from now, and then that value will also be able to put into this carbon monoxide to figure out what the carbon monoxide is changing at in terms of 3 years from now. So, excuse me, this is going to be a composite function. Okay, if you guys remember our chain rule to solve this, again, if we have h at x is equal to f at g at x, then our h prime x, let's move that over, is going to be equal to the function of our original function, derivative of our outside function, multiplied by derivative of our inside function. Okay. Well, think of our carbon monoxide detector here, our equation. This is going to be the f at x of our equation. And our population rate changing is going to be the g at x of this equation. So our population is going to be changing, and so is the carbon monoxide rate. So this is a chain rule function. We have to derive one function within the other function. So when we go to do that, we have to derive our outside function. I'm going to leave the first function, our f at x in this case. So our f at x, we're going to write this as h at x is equal to, I'll write it as a function. Our h at x is equal to technically just this here. Okay? This is our root 0.5 p squared plus 17. And the reason our h at x is essentially just this function is because the p is the g at x inside the function. And the p has a whole nother equation with it. So when we go to find h prime x, we're deriving this function here. Now, we know this is a root, so it's technically to the power of a half. Okay? So that in itself makes us do two parts in order to solve this. I'm going to rewrite this part over here. Technically, this is h at x is equal to 0.5 p squared plus 17 to the half. Okay? And this is why we're not plugging in, even though I showed you that other way. We're not going to plug in a value for p of this equation. Okay? Because it's going to make this far more complex. So we're going to solve this in terms of two different variables and then solve for a specific point. So because this is like this, we're going to use our power of a function rule to solve this when we derive it. So we're going to get 1/2 multiplied what's originally inside the equation, plus 17, then times the derivative of what's inside the equation. So when we derive what's inside the equation, 0.5, we bring the 2 down. 1/2 times 2 gives us 1. So we're essentially just multiplying by a value of p. All right. Yeah, looks good. Okay. And then, what's that? Oh, yes, thank you. The -1/2. Right? When we bring down the half, we have to subtract by 1. We continuously forget to do that. And then we have our p. And then we still have to multiply. This is what we've only done here. This is our f at prime with the original function. Okay? The original function being p. We solve this in terms of p. We still need to multiply by our g prime x. Okay? Well, what that is that's this function here. So we have to derive what's up there. Our 3.1 is going to give us a 0 when we derive it. And when we multiply this down, we're going to be multiplying by 0.2t. Okay? That is going to be our g prime x. So now we have the derivative of this function. And we can go about simplifying a little if we like. We're kind of left with what we got here. Okay. Now, we don't need to simplify because they've actually given us a second part of this question. The second part of this question was, what will the rate of carbon monoxide level be changing at respect to time 3 years from now? So in other words, they're asking when x is equal to 3. So they've asked us, what will the carbon monoxide be changing at when x equals 3? Okay? Or sorry, not our x in this case. X being 3 years from now, well, we know that actually stands for our t, when our t is 3. So we know we can plug that into this part of the equation, but we have a p in terms of the rest of this, so we actually have to solve for p in terms of t. Okay? I'm going to zoom in a little. So we know we have t being 3 years from now, but we also know equation p at t. Well, since t is 3, the original equation p we're going to plug into, which is 3.1 plus 0.1 t squared. And instead of writing the t, we're going to write 3 squared. So our p value is then going to be 3.1 plus 0.9. That gives us 4. So our p value, if our t is equal to 3, the p in this equation will be equal to the number 4. So we're going to plug 4 in for both of the p's in this equation, and we're going to plug 3 in for the t in this equation. So h prime x is a half 0.5 times 4 squared plus 17 to the negative a half multiplied by 4, which is our p, multiplied again by 0.2. Our t value is 3. Now we just have to go about equating all of this. This is all technically above. This is technically 1 over 2 times the root of 4 squared is 16 times 0.5 is 8 plus 17 is 25. And this becomes 4 times 0.6, which is, I think, 2.4. Should be 2. So we can simplify this to read 2.4 divided by 2 root 25. 2.4 divided by 10. Is it 0.24? Yeah. So what this says in our question is that the carbon monoxide rate is changing at 0.24 parts per million 3 years from now.